This second part of 12.1 is going to be about a topic called the inverses of functions. And this is kind of an interesting topic because part of it is really instinctive and easy, and then the fancier, more difficult stuff is where it's going to tie into part A of this topic. Composition of functions will be related here, but not at first. So the basic idea of inverses of functions is an inverse of a function should do the opposite thing that the other function does. It should undo. So if you're imagining working on a computer, say, and you're writing an essay and you make a big mistake, like you're trying to move a paragraph from one part of the essay to the other, but you accidentally hit delete, thank goodness there's this button that says undo, and whatever thing you just did that you wish you hadn't done, it reverses it. That's what we're trying to do with composition of functions. We're trying to come up with another function that will do the exact reverse of what the first function did. So, in many cases, you instinctively know what the inverse function is. Like if I say, okay, like this first example here, x plus 5. What's the opposite of adding 5? Well, don't overthink it. It's exactly what you think it is. The opposite of adding 5 is to subtract 5. So a function that takes a variable and adds 5, its inverse will be to take the variable and subtract 5. Those do opposite things. The notation for an inverse function is something I really wish I had a time machine and I could go back in time and I could change this notation. But unfortunately, I didn't get to invent mathematics hundreds of years ago. We're stuck with this notation. It looks like this. So the original function was called f. The inverse of the function is a related thing. It's not completely random, so the f is still in there. But it's got this little -1 that looks an awful lot like it's an exponent, but it's not an exponent. It looks like an exponent, it feels like an exponent, it's placed like an exponent, but it is not an exponent. If it was an exponent, then your answer would be 1 over x plus 5, because -1 exponent means 1 over, and it doesn't work at all. So please understand that this is a very bad choice of notation. There really should be a symbol there that does not look like an exponent, but I didn't invent math. I'm just teaching you what other people invented, so we're kind of stuck with it. So aside from the notation weirdness, the basic idea should be pretty straightforward. Like if your function g takes a variable and multiplies it by 3, well, what's the reverse of multiplying by 3? What would undo a multiplication by 3? And don't overthink it. It's exactly what you think it is. The reverse of multiplying by 3 is to divide by 3. And for this next one down here, the reverse of x squared, squaring something, the reverse of that is to take the square root. So most of the time, your inverse functions are very easy to figure out. They're what you would think they would be, until you start talking about functions that do more than one thing. Like if you just add 5, then you can simply subtract 5. If you just multiply by 3, then you can simply divide by 3. But what if you do both? What if you add 5 and multiply by 3 both in the same function, like this middle example here? It might feel instinctively like what you can do is just divide by 3 and subtract 5. And if this function multiplies by 3 and adds 5, the reverse should be divide by 3 and subtract 5. But that's actually wrong. That is not the correct answer, and let me show you why. The whole idea here is this function is supposed to return you to what you had before the first function did its thing. So let's start with a number. Let's pick some number to start with, like 4. And really, it could be anything. And if you really want to understand this, you should try plugging in a variable like a. But I'm going to use a number just to make things easy. We're going to take that number, and we're going to plug it into the original function. So take 4, plug it into h. So 3 times 4 plus 5. 3 times 4 is 12 plus 5. You get 17. and then take that 17 and plug into the thing you think is the inverse. And if it's doing what it's supposed to be doing, it should take you back to 4, right? You started at 4, then you got 17. If you want to go backwards, you should go from 17 back to 4. But it doesn't. If you take 17 and plug it in here, 17 divided by 3 minus 5, is that equal to 4? No, not even close. It's nowhere near 4. So what that means is this thing we think was an inverse, it's not an inverse. That's the wrong answer. So, okay, well, what's the right answer? I'm sure you want to know. What is the right answer if that's the wrong answer? Well, the right answer, it's not that hard to figure out as long as you don't just look at the operations, multiplying by 3, adding 5. Also notice what order those operations happened in. When you plugged into h, what was the first thing that happened? Adding 5? No, multiplying by 3. What was the second thing that happened? Then you added 5. So you plugged in for x, you multiplied by 3, and then you added 5. So the inverse function will do the opposite operations, but it'll have to do them in the opposite order. So we're going to have to first subtract 5 and then divide by 3. So you do end up subtracting 5. You do end up dividing by 3. But pay attention to the order, and you'll get the inverse function worked out just fine. Go ahead and test that one if you'd like. You can pick a number, plug it into h, take your output like 17. 17 minus 5 is 12. 12 divided by 3 is 4 again. You know, try it with a few numbers, or if you really want to test it out, try it with a variable. Plug in a to this, and then take the results and plug that in there, and see if you get back to a. That's how you would verify that that thing is actually a function. Oh, wait a sec. Let's talk about that a little bit. Take a, plug it into the original function, and then plug that into the inverse function and see if you get a. That's the test. That's the test of whether something is an inverse function or not. And look what's happening there. That's composition of functions. So this is why this is in section 12.1. We learn about composition of functions because you need composition of functions to talk about inverse functions. The way you test to see if something is an inverse is you compose the function with the supposed inverse function and see if they cancel out to the original letter. Okay, there is one other key difficulty with inverse functions. Sometimes if they have a single step, like on the left, you can figure out their inverse instantly, instinctively. If they're a little bit more complicated, if there's multiple operations, you have to pay attention to the order, but you can still kind of reverse every operation. But like this one we've got over here on the right, some functions have multiple things happening at the same time to where you really can't say which one happens first and which one happens second. Do you add 2 first and then take the result and subtract 3? No, that's not right. Do you subtract 3 and then take the result and add? No, that's not right either. You know, it's kind of hard to even describe what's happening first and second and third and fourth in this operation. So how do we find the inverse here? Well, now we're going to have to get fancy. What we're going to have to do is we're going to have to talk about what an inverse is supposed to be doing. It's supposed to be taking what used to be the output, like over here we had 17 was the output, and treating it like the input. And the input, 4, is what we anticipate for the output. So it's basically switching input and output. Output becomes input, input becomes output. In an equation, the input is x, the output is y. What that means is we're going to switch x and y. Take your inputs, turn them into outputs. Take your outputs, turn them into inputs, which means the equation's now going to look like this. and I can still remember the first time I was taught to do this kind of thing, my reaction was, that doesn't really make any difference. Nobody cares what letters you use. How is this actually finding the inverse? And it's kind of weird. This actually does find the inverse as long as you realize this needs to be simplified. We normally don't write equations with x by itself. We normally write our equations with y by itself. So what you have to do now is solve for y. Take this equation we've created and solve it for y. Okay, so let's see. How am I going to solve this for y? Well, I'm going to multiply up the denominator, because I don't like fractions. And then I'll distribute in that x, because I don't like parentheses. And since I'm trying to solve for y, I want all the parts that involve y to be put on one side. So this y here, I'm going to move it over to the left. And anything that doesn't have y, I'm going to move it over to the right. So I'm going to end up with xy minus y equals 3x plus 2. And now to finish solving for y, I'm really actually almost done. I factor out y, and then divide by that x plus 1 thing, and I'm done. So what was the letter we started with? It was, that was t of x. So this is going to be t inverse of x equals 3x plus 2 over x minus 1. And if you want a real interesting challenge, try using the inverse test on that combined with the original function and see if they do indeed cancel out. I promise they will. It's just kind of an interesting little challenge to do it. In fact, while we're talking about that, let's try using the inverse test on this example we had over here. Because you'll notice, I put a box around all my answers except that one. You might have been wondering, why did he do that? There's actually a reason why I didn't put a box around the answer there. If I take k inverse of k of a, that means I'm going to be doing the square root of x squared. Does that come out to be x? Think back. Think back to when we were learning how to work with roots. You might realize, oh my goodness, there's a problem here. The square root of x squared is not x. The square root of x squared is the absolute value of x. And what that means is, your instincts are sometimes wrong. What's the opposite of squaring something? Well, taking a square root, sort of. And this is actually a really important example, because think about plugging a number into the original function, like 7. 7 squared is 49. And then you would say, okay, if I've got 49, how do I get back to 7? You take a square root. But if I tell you the output is 49, do you actually know that the input was 7? Couldn't the input have been something else? Couldn't the input have been negative 7? So the problem with this function here is once you have an output, if I say the output is 49, you actually don't know what the input was. There's more than one possibility. The input could have been 7, or the input could have been negative 7. And what that means is this thing actually does not have an inverse. Some functions don't have inverses. So then, of course, you want to know, when do I know if something has an inverse or not? And it turns out there's a thing called a one-to-one function. What we want to avoid is what we just saw happening there, where one output had two different inputs that produced it. 49 came from both 7 and also from negative 7. So you don't want that happening. This is the description of that not happening. A function is one-to-one if no two inputs share the same output. And what that means is only one-to-one functions have inverses. If something is not one-to-one, it does not have an inverse. Well, okay, how do I know if something's one-to-one? It's actually pretty easy. If you look at that definition, it should look kind of familiar. It's not the same as the definition of a function, but it's related. The definition of a function was you can't have a single input with more than one output. This says you can't have a single output with more than one input. And with functions, we had a vertical line test. Here we have something called the horizontal line test. If you have a function like this, y equals x squared, and you can draw a horizontal line through it at, say, 49, where there's 7, 4, or negative 7, 49, and positive 7, 49, then that is not one-to-one. So if you have a graph that looks like, say, this, that one is going to pass the horizontal line test. This one is one-to-one. Whatever the heck it is that gave us a graph that looks like that, I know it has an inverse. On the other hand, if I've got a graph that looks like, say, this, just like with the vertical line test, one bad spot ruins it for everything. Same idea with the horizontal line test. Draw a horizontal line there. It hits there, there, and there. All of those points are the same output, but they have different inputs. That thing is not one-to-one. Okay. Our next video is going to be about some very important issues related to inverse functions. Please watch that one next.